Quadcopters are incredibly effective and flexible UAVs, but as more and more drones get launched into the air, it's inevitable that some will cross paths. How does that affect a drone's aerodynamics? Does being in the vicinity of another drone help its aerodynamics like a bird flying in formation, or does it hurt its aerodynamics? That is what we're looking at today. And to do that, we're looking at this paper called, if I scroll up, Multi-Drone Aerodynamic Interaction Investigation. And this is open access, so you can find it in the link below. Now, if flying close to each other is good for drone aerodynamics, then you could do things like extend a drone's range by making it fly in a posse. If, on the other hand, flying next to another drone is bad for its aerodynamics, then you'll want to make your drone a loner and avoid others like the plague. To find out which is the case, this research uses some pretty high-tech equipment. For example, in figure 2 down here, we see they use something called stereo particle image velocimetry, or stereo PIV for short. What that is you have two cameras spaced, here we go, like right here, a certain distance apart, and then these cameras are focused on the exact same region. So this like blue SPIV plane here. So in effect, you have these two cameras looking at the same thing, but from different views. By shining a laser sheet through this region that they're focused on, and then dumping some kind of particles that reflect the laser light, the cameras can now see the flow, what it's doing at that moment in time. The major benefit of having these two cameras spaced apart like this is, unlike a regular PIV, where you have only the particles in two directions that you can determine what the velocities are, now you can kind of see it in three directions. And as such, you can figure out how fast the particles are moving in these three orthogonal directions, so X, Y, and Z. And that is done by simply taking two pictures in succession, then tracking where these particles go in the time between these two photos. We know that the velocity is divided by the distance divided by the time, so you know the distance and you know the time between pictures, so Bob is your uncle. While this process sounds very simple, and in a way it is very simple, the main difficulty is in the errors in the setup. So for example, synchronizing the cameras is a real pain and you need to be very precise with the timing. That's why you need very specialized timing equipment. But then if you take too long between the two pictures you take in succession, then many of the particles you photographed in the first image will have passed through the laser sheet and will no longer be visible. And to add to that problem, more particles that weren't in the first photo will now be in the second photo as they have now entered the laser sheet during that time. So there'll be all this information that doesn't really mean anything, and so that manifests itself as simply noise in the data. That makes trying to process the data far more difficult. As such, you need to have two pictures taken very quickly in succession so that most of the particles are still in the laser sheet during both photos. And that brings us to another difficulty. So you might have a camera that you can do some pretty high speed stuff with, like maybe 600 frames per second or higher. Like I think iPhones these days can do like 480 FPS or whatever it is. That's really high. But in some cases, that's not really applicable. The problem is that with those cameras, they may be operating in something called a rolling shutter mode. What that means is that line by line, the camera takes a photo. As such, when you get a picture from that camera, you're not actually getting a snapshot in time. What you're actually getting is each line occurring at a different time to the next. And as such, this photo skews the data. So you actually need a camera that operates on something called a global shutter, because how that camera works is exactly how you'd expect it to work, where every picture is taken, the pixel in each picture is taken at the exact same time. So global shutters are much slower, and that is because there is far more information that needs to be dealt with at the time of the snapshot. The processing unit then needs to process all this data at the same time, and that reduces the rate at which the camera can take pictures. So overall, when doing PIV, there are several key factors that need to be kept in mind in order to get high quality data. So let's move on from these general ideas. Anyway, so the researchers were very interested in to see how the tip of one drone affects the tip of another drone in terms of aerodynamics. So they focused their PIV efforts on this region between the two drones. So you can see here, if I zoom in, to the left here, we have two drones, one in gray, one in green. As they spin along, this snapshot here is focusing very much on the tips. And then this little figure down here shows these two tips as well and the distance between them potentially. So this is a really important region because the blade tips produce vortices, and the way one vortex interacts with another might actually make each propeller more efficient, or it might not. We have to see. Now in table 2, we see the various conditions that the drones were tested in. So here we go. First of all, each drone had rotor blades, or I guess you could just say there were two rotor blades, and each rotor had two blades on it, which is very common. Now, the blade profiles were NACA 0010s, so that means that they were uncambered, so unbent, and they had a thickness of 10% of the chord. Now, NACA 0010s are pretty rare for small blades, for small drones. Usually you're looking at more cambered ones, so you'd have some sort of camber as opposed to uncambered. Anyway, the chord was 0.019 meters, so that means that the radius of the blades was 0.136 meters, so about 11-inch rotor diameter, which is pretty large actually. So the ones like DJIs and that, they're usually more like 5-6 inches, so that's about twice as much here. So the blades here were also untwisted, and this piece of information is quite important because if a blade is untwisted, then there is a very good chance that there will be strong tip vortices. The only common way to reduce the tip vortices now would be to taper the blades so that as you get closer to the tip, they get smaller. But in figure 2, we see that they are not tapered at all. So we can safely conclude that there will be some kind of strong tip vortex from each blade. Now, they tested the propellers at two different Reynolds numbers, 40,000 and 80,000. Both of these values are well within the laminar regime, so it will be interesting to see if there is any difference when you double the Reynolds number here. Usually, propellers are more sensitive to the Reynolds number when you are at low Reynolds numbers like this. Then they tested a few different distances between the propellers. So they annotated this by the the letters AS. So AS stands for axis shift. And the greater this number is, the further the distance is between the two rotors. And well, they went from 2.1 times the radius of the blades to 2.5 times the radius of the blades away. So what that means is that when you have a value of 2.1, it means that the centers of the propellers were separated by 2.1 times the radius of the propellers. So that means that there was only a 10% of the propeller radius distance between the tips. So they're very close. And then when it's 2.5 times, then that's still really close. And it can also start to approximate a drone when the propellers are just very close together. So for a quadcopter, you obviously have 4 drones dotted around the drone. Now, depending on how close they are together, you have a certain amount of interaction. Now, one thing I should mention is that having the propellers on a drone very close together is not exactly the same as having 2 drone propellers close to each other from 2 different drones, potentially because if you have these 2 different propellers from different drones, they may be spinning in the same direction as opposed to opposite directions, which is what you would get on a drone propeller, on a drone regularly. If you have one drone, 4 propellers, each propeller is spinning in the exact opposite direction from the 2 propellers adjacent to it. So that's very important to note, as we'll see later at the end of this podcast. So anyway, the literature generally says that you want to place your drone propellers about 3 radii away from each other. That isn't a hard and fast rule, but approximate. So at 2.5, this is very close to the lower limit, and I'll be really interested to see if there are any effects here. In the next section, they do a great job quantifying the errors in the PIV results. So this section here is 2.3, uncertainty estimates. This is something that is rarely done in PIV, and really with all data in general, unfortunately. Now, I'm not going to go through the whole uncertainty estimation because we've gone through something like this a few times in other podcasts. But I just want to quickly explain the interrogation windows, what they're talking about here. So they say, for example, here, interrogation window. There's another one around here. Oops. So anyway, with any digital camera, you have a certain number of pixels in the photo. To reduce error in PIV, you typically break the photo up into something called these interrogation windows, which is just a square of a certain number of pixels. So here they have various interrogation windows from 64 pixels by 64 pixels, 32 pixels by 32 pixels, and then even something resulting in 16 by 16 pixels. So these are very common values, and that means that if you have your picture, you're breaking the picture up into squares, and each square is 64 pixels wide by 64 pixels high, or whatever numbers you want to use, whether that's 32, 16, 98 is another very popular one, and 120 is also pretty popular as well, or 128. Anyway, so the reason why we do that is because you really don't know how many little particles you'll find in each window. Sometimes the particle density is super high, and you might want to drop their interrogation window down to 16 by 16 pixels because there's enough information to determine what the float is doing at this resolution. Other times, there aren't enough particles in your interrogation window, and you need to increase the size to maybe 64 pixels by 64 pixels or higher just to get a decent result. So when you read through this section, that is what they're referring to when they say these things. So they're also talking about doing multiple passes to whittle down the errors as you go finer and finer with your interrogation window. That's actually a pretty clever idea. Anyway, Overall, for their forces, they concluded that their thrust and torque measurements have a standard deviation of 4% and 3% respectively. So what that means is that the uncertainty to within a 68% confidence interval is 4% and 3% respectively for the thrust and torque measurements. Now the figure of merit, which is a single value that you give to say how good a propeller is, had a maximum uncertainty of 9% that they say here. Now, I don't know exactly how they calculated that or what they mean by the maximum uncertainty. The reason why that is important is because they give a 68% uncertainty interval, or confidence interval, for the thrust and torque. And then if you're giving something like a 99.99999% uncertainty for the figure of merit, then there is some inconsistency there, and that 9% value could probably be brought down a lot by adopting a more reasonable uncertainty level. They just don't say what it is here, so I'm not exactly sure. Anyway, for the PIV, they say that the instantaneous velocities are within 6% of the means. Again, I'm not too sure what the confidence interval is of this number, 6%. Let's now move on to the results. So in figure 3, we see the figure of merit, and for two different Reynolds numbers, and the x-axis is the axis shift as a function of the propeller radius, where 2 means that the propellers will be exactly like literally just touching as they go by. 2.1 means that there's just a fraction of a distance between them, so 10% of the radius. And 2.5, as I mentioned, there's about 50% of the radius between the two propeller tips as they circle around. So in equation 2, we see how they calculated the figure of merit. And in layman's terms, the figure of merit simply tells us how much energy is required to hover compared to how much energy in theory it should take. So in reality, because of inefficiencies, you're always going to need more energy than theory says. So this figure of merit will always be less than 1. And this figure of merit idea applies pretty much to anything that hovers. Like you can apply this to helicopters, drones, whatever you like. And this is a very common number and has been around for a century or so. So something that is a little unusual about this equation is that it combines both the left and right propellers together. And that's given by the subscripts L and R. So the CT value is the coefficient of thrust, and the CQ value is the coefficient of torque, and these are just standard terms. And CQ always is just weird because, like, why would you use a Q here? But obviously you can't use a T because that's taken up by the thrust. So you just have to remember that CQ is always the torque, which goes for helicopters as well. So anyway, the authors have done a nice job putting the error bars on these graphs, which you rarely see, and this is a really good practice. So I'm really happy with that, and that's really cool. And everyone should aspire to do this too. So looking at the blue line, which is the 40,000 Reynolds number, as expected, as the propeller moves further and further away from each other, the general trend is that they become more efficient. The figure of merit goes up. However, strangely, as an axis shift of 2.2, the lowest figure of merit value is seen, and it drops by quite a lot actually. So like, what's that, maybe 20% overall almost, compared to 0.35. Then when you put the propellers even closer, that figure of merit value jumps up again. Now, we haven't seen the flow vis yet, so I'm not sure exactly what's going on, but I think that it's probably something to do with the major aerodynamic problem here, is that the axis shift of 2.2 isn't necessarily a hard and fast value that every propeller will experience. In fact, I think that perhaps every propeller will have a value around this perhaps where the figure of merit will drop, but it is likely different for each propeller couple. So maybe it might be 2.25, 2.15, 2.1, 2.3, depending on the propeller. Anyway, in terms of the changes to the figure of merit, we're only talking like a few percent anyway, generally speaking. This one is just really an outlier. So that's good news in that there isn't that much to worry about if your propeller comes close to another propeller. Now, when the Reynolds number is 80,000, so it doubles, the graph looks quite different. In fact, you could argue that increasing the axis shift is actually worse, as long as you can see here that we have lower values, and the figure of merit is definitely higher when we go to lower axis shift values. So I think that perhaps this is something to do with the interactions between the tip vortices, and there is some cancelling out going on to increase efficiency as we get lower, but we'll have to wait and see what's going on. Actually, let's not wait and see. Let's see them now in figure 4. Here we go. So here we see the instantaneous vorticity fields. And now, strictly speaking, these blue and red dots are not necessarily vortices. Just because there is a very high vorticity in each one of these centers doesn't mean that it is, but it is very likely that they are. So the left column is for a Reynolds number of 40,000, so these ones here, and then the right column is for a random number of 80,000. Now, we see a major difference in the flow fields. Let's concentrate on when the axis shift is 2.1 times the radius, so these top two. And when you have a random number of 40,000, so this left one here, the vortices from each propeller tip are far greater in number than when the random number jumps to 80,000. And if you look at where the vortices are originating on the blades, at 40,000, let's zoom in a little bit actually, here we go. There we go. That's much nicer. So we can see here, at 40,000 you can see that the vortices occur much further inboard from the tip than at 80,000, which are closer to the tip. And then at 40,000 you can see that they're breaking down as you go further down, which is why we saw that rise in figure 3 when we get the axis shift of 2.1 for the blue line. So that makes sense. Now keeping an eye on the left column, we see what happens when the axis shift becomes larger and larger. So each propeller acts more like they are just in free space. For the right column, a similar thing happens, but to a far lesser extent. But remember that these are instantaneous snapshots, and perhaps these photos are just luck of the draw. So let's move on to the average ones in figure 5. So here we see the average flow fields, the streamlines here, and the velocity ranges from 0 in blue and 3.5 meters per second in red. Now we see the really big difference between cases 40,000 Reynolds number and 80,000 Reynolds number for a axis shift of 2.1. So the tips are almost touching here, and then the weight from both the propellers is far greater for the lower Reynolds number than for the larger Reynolds number. That right there is a major reason why the figure of merit is so much higher for the high Reynolds number case. It's because this wake is much smaller, there's far less loss going on. And why is that occurring though? Well, it seems like this has a lot to do with how fast the tip vortices are being shed from these tips. And for the lower Reynolds case, the vortices are definitely hovering around more of the tips. So you can see here they're really rolling up on average. So that suggests that it takes longer for them to flow away from the tips. But in addition to that difference between the 40,000 and 80,000 Reynolds number cases, it is also interesting just to see how much the wakes are skewed. So the left side is much straighter, and even it flows to the right a little, while the right side flows really to the right and is very curved. So that direction, that occurs because of the directions that the propellers spin. That then indicates that while this research could give some good insight into what is happening for two propellers on the same drone interacting with each other, as I mentioned earlier, if you have two propellers on the same drone very close together, this is pretty somewhat applicable, but it isn't an exact replication of those conditions because any two neighboring propellers on a drone are spinning in the opposite directions, which means that when the tips swing past each other, they're swinging in the same direction. So I don't think that this asymmetry that you see here will occur on a drone when you just have these two propellers very close to each other. This asymmetry is very much because you have two drones next to each other and the propellers are spinning in the same direction. Anyway, let's now look at how each Reynolds number independently from each other changed the flow field with increasing axis shift. So the left column, let's zoom out a little bit so we can see a bit more here. Okay, so here we go. For the left column, which is 40,000 Reynolds number, remember, and back in figure 3, we saw that there was a global minimum for this figure of merit when the axis shift was 2.2, and it was quite a large global minimum. And then there was a general trend of when the axis shift increases, so does the figure of merit a little bit. So that would explain this, would be explained in these plots where if we look at the axis shift of 2.2, which is this second plot here, the wake is arguably as large as when the axis shift is 2.3, because while it isn't as wide, it extends further down, I think. So that would explain the sudden drop in the figure of merit that we saw for an axis shift of 2.2. And comparing the 2.2 to 2.1, the wake is like 4 times or 5 times as large. So just a small increase in this axis shift resulted in a huge increase in the wake size. So that's kind of consistent with this figure of merit drop. And what's more, it seems like there are 2 consistent vortices from each tip intact. Let's zoom in a bit, here we go. So 2 vortices intact from each tip, one at the top, one at the bottom. Then for the other, and you can see these 2 lower ones here, for all the other axis shift ones, these vortices aren't nearly as prominent. Here in the top one, there's no vortices. In figure 2.3 axis shift, there's maybe one present that just is consistently there, as is for an axis shift of 2.4. What that tells me is that for this axis shift of 2.2, the tip vortices aren't breaking down as quickly as for the figure of merit increasing with the general axis shift increase. I can kind of see that from these wakes too, because you can see that for the 2.3 and 2.4 axis shift ones, the vortices are pretty much the same. And I actually don't think that the wake is that much greater for the 2.4 one, because yes, the flow between the two tips is much slower. It's like getting down to like, what is that, 0.5 and less meters per second. But the flow around the wakes, the outsides of the wake, is much faster. And I think that cancels out a little. And the flow between the two tips as you go down is actually very straight. So not very chaotic at all, as you might expect from a wake. And again, this is average. So I think that perhaps while there is unsteadiness in this wake, overall it cancels out. So the fact that this figure of merit increases to me makes sense after seeing these plots here. Now let's jump to the right column, because this is where we see the Reynolds number of 80,000. Now remember from figure 3 that as the red line shows here, if I scroll up, you could argue that as the axis shift reduces, the figure of merit kind of increases a little bit. At least, at the very least, there is a global minimum at an axis shift of 2.3, which is the middle value tested. And again, it is a drop here, which is reminiscent of this 40,000 Reynolds number 1 as well. Anyway, I think that these plots in figure 5 explain a lot of this slight increase as you reduce the axis shift. Whereas, here we go. So we see that going from an axis shift of 2.2 to 2.1, so from the second plot to the first plot, the wake gets much smaller, more small than you might expect really. And that is a good indication as to why the figure of merit is now better. But then remember that axis shift of 2.3 was a much worse one, and the plot here shows just how much worse the wake is too. It's huge. So on average, it seems like the vortices have broken down, or at least at the very least, they meander around very chaotically. So the flow is also much slower, and the velocity around the edges of the wake isn't that much higher either. So I think that we can conclude that the tip vortices here are negatively interacting with each other, so that produces a larger wake. And then as axis shift jumps up to 2.4, the wake again could be argued to not increase that much in size, because again, it seems like the velocity on the outsides of the wake is a little higher, and the inside of the wake, okay, the flow is very well behaved, and the velocity is perhaps a little bit lower. So there's some kind of cancelling out in terms of the positives and the negatives, I think. So I think here perhaps the vortices aren't really interacting with each other too much. We're just kind of working among themselves, really. So let's skip over figure 6, because I don't really like these plots. The way they've set them out, it makes it really hard to compare the same Reynolds numbers at different axis shifts. It makes it easy to compare the same axis shift at different Reynolds numbers, but the results are kind of expected, where the higher Reynolds numbers just pull in more error. Anyway, let's go on to figure 7. So in figure 7, we see this figure that shows an idea as to what is happening when the propellers get close to each other. The left figure is when they are quite far apart, and here the vortices from the tips are allowed to continue on their merry way without any interaction with their counterparts from the other propeller. For the right figure though, that is not the case. The propellers are now close enough where there is a significant interaction between these vortices, and that is not always a good thing, as we saw in figure 3. Now, after seeing this data, one potential solution that comes to mind is to duct the propellers, so to put a ring around each propeller. That not only helps keep the flow around it separated from each other, but also reduces the chances of getting a tip to the eye, which no one wants. While this research doesn't cover that idea completely, in table 2 they do give some general numbers as to the different figures of merit for a drone with and without ducts. And generally, ducts do improve the performance of propellers, but not always. It depends on the duct geometry, and the reasons for that we'll need to cover in another podcast. Anyway, in this table here, ducting the propeller greatly improves the figure of merit for low RPMs. But that advantage, for this quadcopter at least, disappears at RPMs which are quite high and very quickly. And then in figure 8, we can see how, if we scroll up, zoom in a little bit, here we go, we can see that for the ducted propellers, the vortices remain more distinct and separate from each other, as you might expect. So they're really just being channeled down more, and they're not being allowed to interact with each other as much, which really explains a lot of the increase in the figure of merit as well. So perhaps the solution is to increasing these propellers' efficiencies when they're close to each other is placing many ducts around the propellers, many tasty ducts. And that brings us to the end of this podcast. If you liked it, hit the like and subscribe buttons. And while this research wasn't done with CFD, if you want to learn how to do CFD and in particular OpenFOAM, which if you were to learn, you could then do the exact same setups, but with CFD, which would give you even more data, then take our course and link below. And if you're staying on YouTube, YouTube thinks that you'll like this video, so check it out. Peace out, amigos.